Hello, in this video I'm going to explain an algorithm to detect the similarity of matrices. But what is the similarity of matrices? In linear algebra, two n by n matrices A and B are called similar if there exists an invertible n by n matrix P such that B equals P inverse AP, or equivalently P A P inverse. So this is the definition of similarity, but I needed an algorithm in C# that can detect if two matrices are similar. I tried to improvise an algorithm. This is what I have done. There may be better algorithms. This is just what I found. Suppose that A and B are two n by n square matrices. Here I prefer to use lowercase letters for matrices. For some reason, I use lowercase letters for convenience. Are these two matrices similar? That is there an invertible matrix X with same dimensions such that A equals XB X inverse? Let's improvise an algorithm that checks if A is similar to B. First, we have to solve the equation AX equals XB. Here, we want to check if there is some X that A equals XB X inverse. But if there is such X, then AX equals XB. So if we find all solutions of this equations for X, then we can check which of these solutions is invertible and satisfies this equation. Here we have multiplied both sides with X. AX equals XB X inverse X, but X inverse X is the identity matrix and has no effect. So AX equals XB. First, we have to solve the equation AX equals XB. If such an X exists and is invertible, then B is similar to A by definition of similarity. We can rewrite the equation as follows. AX equals XB implies AX minus XB equals 0. In fact, we subtract XB from both sides. AX minus XB, XB minus XB, which is equal. Here by 0, I mean the 0 matrix, which is an n by n matrix. So it is a matrix with all entries 0. Thus, for every I and j in Nn, we obtain. Here Nn is defined to be the set 1, 2, 3 till n. The first n natural numbers, the first n positive integers. For every I and j in Nn, we obtain. When we write the definition of multiplication of matrices, we obtain this. A is a matrix. The ij entry of this matrix is shown by aij. Now, ax, the ij entry equals, by definition, k from 1 to n, aik, bx, kj. This is the definition of multiplication of matrices. The ij entry is defined with this summation. But we have two multiplications here, and I combine them as this summation. K from 1 to n, aik, xkj minus xik bkj. I could add a sigma here from 1 to n for this multiplication of matrices, but it's not needed. One summation is enough for both because the summation is the same for both. This summation equals 0 for every I and j in Nn, because we know that this matrix equals the 0 matrix. So this number, which is an entry of this matrix, equals the number 0. Here 0 is the number 0, unlike this 0, which is the 0 matrix. This is a system of linear equations with unknowns xst. The xij or the xst here that appears in these equations for every I and j are unknown. We are going to find them, and we have these equations, a system of linear equations, and we have unknowns. I'm trying to reach a matrix equation for this system of linear equations. So I define the new unknown x as an n2 by 1 matrix, such that for every s and t in n, x s minus 1 times n plus t equals xt. Here, x is like this: x1, x2, and here xn to the power of 2. A long vector matrix, a column matrix. It's n2 by 1, and it is defined to be x1, 1, x1, 2, x1n, and then x2, 1, and this process continues. And if we try to find a more precise definition, we get this: x s minus 1 times n plus t equals xt for any s and t in n. You can check that x is well defined with this definition. Now for every I and j in n, we rewrite this equation here, and we replace xkj with this. If s is k and t is j, we get xk minus 1 n plus j. And here, instead of xik, we use this definition and write xi minus 1 n plus k. And these two numbers are interchanged because they are real numbers. But what is the coefficient of the unknown xr in the above equation? Let's find this coefficient. If p is a proposition, some statement that is true or false, we define delta of p equals 1 if p is true and 0 if p is false. The negation of p is true. I can write it like this: if p is true, if p is false. Assuming I and j are constants, for every s in this set, that is the set of all numbers 1, 2, 2, and 2, these n2 numbers. For every s in this set, s equals this if and only if k equals this. This is the index of x in this equation. We need to replace this with s. S equals this if and only if k is like this. Also, s equals this, which is this index, if and only if k is like this. So, if this k is from 1 to n, that is, if k is in this set, because here k is from 1 to n, then we have this index, which we show it by s. Also, if this k is in nn, this will be an index of xs. What is the coefficient of xs in this equation? If this equals s, the coefficient of xs will be, by this equivalence, ai s minus j over n plus 1. Instead of k here, we use this. So if this index is s, its coefficient will be ik, where k is of this form: ai s minus j over n plus 1, provided that k, which is defined here, is in nn. So we multiply this coefficient with this delta s minus j over n plus 1 in nn. If this is not true, this will be 0. And when this is 0, all this will be 0. Mathematically, this is not a correct form of writing this number because this may be undefined. If it is, for example, a number that is not in nn, this will be undefined. But programmatically, algorithmically, if this is 0, this will not be calculated by the algorithm. So this is not mathematically acceptable to write like this, but programmatically there's no problem. We know what this means. If it is in nn, it will be 1, and this is defined, so we know that all this number is defined. The same for this number. If this number is in nn, then this number b is defined, and also all of this is defined. If this is false, this number will be 0, and we ignore the second term, which may be defined or undefined. So if this equals s, this coefficient will be like this. Also, if this equals s, this coefficient will be like this. If s equals both of these, then we will have aik minus bkj. If s equals this only, we will only have aik. If s equals this, we will have minus bkj, and if s is none of these, we will have 0 for the index of xs. So we now know what is the index of xs in this equation for any s in n index n2. We show this index by this number. In fact, this can be shown by a number like this, bijs, with 3 indices. But instead of ij, I have used one index, I minus 1 times n plus j. So A has 2 indexes. We can show this with t here like this, ATS. Now ATS is defined. Thus, for t equals this index, the above equation can be rewritten as, this equation can be rewritten as s from 1 to n2 ATS, which is the index of xs, times xs. The index of xs in this equation is ATS, where t is defined with this. We assume that I and j are fixed, are constants. Now we forget that assumption. Now, for any I and j in the set n, we get a t in the set n2. For any I and j, using this equation, we get a unique t. And for any t, there are unique I and j's such that t equals I minus 1 times n plus j. In fact, there is a one-to-one correspondence between n times n and n to the power of 2. To prove that this gives a one-to-one correspondence, we can use the division theorem. Euclidean division is based on the following result, which is sometimes called Euclid's division lemma. Given two integers a and b with b non-zero, there exist unique integers q and r such that a equals bq plus r. Q and r here are I and j. You can use that division theorem to prove this one-to-one correspondence. Here I and j goes to I minus 1 times n plus j. Thus we proved that for any t in n index n to the power of 2, the above equation, that is this equation, can be rewritten as this equation. But if we assume that AST is the entry of some matrix called A, this equation can be written as this. The matrix A times the matrix X equals 0. Here I mean a 0 matrix, which is a column 0 matrix. Here A is an n2 by n2 matrix. Why? Because T is an arbitrary number of n index n to the power of 2, and also S is an arbitrary member of this set. Both S and T are in this set, and so A is an n2 by n2 matrix. Now, to find the matrix X, or find all solutions X of this equation, AX equals XB, we need to solve this equation. When we solve this, we can convert this x to this x using this equality. But we know that all solutions of this equation is called the null space of the matrix A. A is a square matrix. I searched for the null space of a matrix. Null space, the null space of an M by N matrix A, is the set of all solutions to the homogeneous equation AX equals 0. So all solutions of this equation is the null space of A. Here in C# I have written a class that represents matrices, and this class has a method named null space that returns a list. The list that contains a base for the null space. You know, null space is a vector space. A vector space with a finite dimension or finite rank. The null space method in this class returns a basis for this space. So I can use this method to find a basis for all solutions of this equation. In fact, we know that this equation is equivalent to this equation. So we will find a basis for all solutions of this equation. And using that basis, we will have all possible solutions. We will find all possible solutions of ax equals xb, what we were trying to find. But there may be infinitely many solutions, but all solutions make a vector space. All we need is to find a basis for that vector space. Here, A is an n2 by n2 matrix. V equals this is a vector space. V is the set of all solutions of this equation. Is a vector space, which is equivalent to the null space of A here. The following C# function finds a basis for this space. I use this method to write a function that solves this equation, that finds a basis for A and then changes this basis to a basis of this vector space, which is equivalent to the null space of A. Let's see. I wrote that function here, but let's read that function in Visual Studio. I named that solve ax equals bx. Here, A and B are matrices, which mat is the name of the class I showed you earlier. Matrix A, matrix B. Solve the equation ax equals bx for x. How does this work? If A row number is not A dot column number, if the number of rows of A is not equal to number of columns of A, that is, if A is not a square matrix, or similarly B is not a square matrix, then throw an exception, kind of error. If A is not squared or B is not squared, this function won't work, will not work. Also, if the dimensions of these matrices are not the same, if A dot number of rows is not equal to B dot number of rows, then also the function will not work. Now, let's show the dimensions of these matrices by n. N equals the number of rows of A, which is the number of columns of A, which is the number of rows of B, and number of columns of B. And n2 equals n times n to the power of 2. We need this number 2. I will try to find the matrix A using this equation and then solve this equation in the function. I'm trying to define ATS, just like this. Here, this is T, and ATS is defined like this. But if we have T, there is a way to find I and J uniquely. Here, I equals the remainder of this division, T minus 1 over n plus 1, and I is the quotient of this division plus 1. I don't explain it further. Let's define the real number del1, which is this number. This is del1, and also this will be del2. Let's find the definition of del1. We define e1, the integer e1, to be 1. Now, if this is an integer, the remainder of this is 0, we define e1 to be this number. In fact, we want e1 with this number, e1. But e1 is an integer, so s minus j over n must be an integer too. So we say that if s minus j is divisible by n, then define e1 to be equal to this. Now, if e1 is between 1 and n, then set del1 equal to this, ai e1. So this part is defined, del1 is defined. If this is not true, then del1 will be 0. If this is not true or this is not true, then del1 will not be equal to this and will be 0 as was defined originally. Also for del2, we define del2 to be 0, but del2 is going to be this number. We define e2 to be this number. In fact, this is e2, but e2 must be between 1 and n. If so, if e2 is between 1 and n, then del2 will be equal to this, be2j, be2j. If e2 is in this set and index n, then del2 will be equal to this. e2 is the same as this, e2. If e2 is in this set, then del 2 will be equal to this. Now ATS equals del 1 minus del 2. We define value del 1 minus del 2, and we set AST equals to val. We could write directly like this. ATS equals del 1 minus del 2. Del 1 minus del 2. ATS. Now the entries of the matrix A are defined. So A is defined, and we need to find the null space of A. We use the method null space. A.null space will return a basis for the null space, and this basis is a list, so we define list equal to this method. Now we have a basis for all solutions of this, the null space of A. But we need a basis for V, which is the set of all solutions of this equation. So we will convert the basis members in this list, which is of the form X, to basis members of this space, which is of the form lowercase x. For any basis in this list, we define the little matrix X, which is n by n matrix, such that AST equals x s minus 1 times n plus t, using this equation. XST equals x s minus 1 times n plus t, which is used here, and then we add this x to the new list, which is going to be a basis for the vector space B. Then we return this basis. So the function solve AX equals BX, this function returns a basis for this vector space. The following C# function finds a basis for this space. They got the knowledge flowing every day, teaching me things in a fun, entertaining way. With this function, we find all solutions of AX equals B. As soon as we have a basis for the space of solutions of this, we have all its solutions. All its solutions are of this form. If T1 to TR is a basis for the space of solutions, any solution is of the form sigma k from 1 to r tk, where tk is a real number. With this function, we find all solutions of this. But the story does not end here. We must determine whether any of these solutions is invertible. We found all the solutions of this equation, but we don't know if any of these solutions is invertible. If any of these solutions are invertible, then A and B are similar. And if none of these solutions is invertible, they are not similar. But how can we check that any of these solutions, that may be infinitely many, is invertible? Suppose we have T1 to TR, this set, as a basis for V. V is the space of all the solutions of this equation. Let's assume that this is a basis for V. Any solution of AX equals XB is of the form sigma k from 1 to r tk, where T1 to TR are real numbers. All solutions of this are of this form. We must see whether numbers T1 to TR exist such that the determinant of this matrix, which is shown like this, is not zero. We must check that if any of these matrices is invertible. Equivalently, we must check if any of these matrices has a non-zero determinant. We define the function f of T1 to TR to be the determinant of this matrix, where the TKs here are the coefficients of the members of the basis. TK is the coefficient of TK. If this function is identically zero for any set of TKs, then there will be no invertible matrix of this form, and so A and B will not be similar. And if there is only one tuple T1 to TR such that f of that tuple is non-zero, then there will be an invertible function x such that AX equals XB. And because x is invertible, then A will be equal to XB x inverse. And so A and B will be similar. Determinant of a matrix has a formula which is called Leibniz formula. Determinant of A equals sigma in Sn, which is the permutation group. Sn is the set of all permutations that is functions n to nn, such that f is invertible, that is f is 1 to 1 and onto, or surjective. All invertible functions f constructs a set which is a group, but that doesn't matter here. All functions sigma in Sn, let's show these f's with sigma. All functions sigma, which are 1 to 1 and onto. The determinant of A is the summation over sigma in Sn of this sine of sigma times the product of a sigma I i's. This is the determinant of A. Sine of sigma is defined somehow, but we don't need it here. Any member of Sn has a sign, which is shown by sine of sigma, but its definition is not needed here. F of T1 to Tr equals this determinant, which by Leibniz formula equals this. Now the I sigma I entry of this summation is this. In fact, this I sigma I is for Tk. All of this equals this if we use the definition of summation of matrices. In fact, sigma A in some set, gamma, ij, the ijth entry of this equals aij. These ij's are for these a's that are in the summation. The same happens here. These indexes are for these tk's. Now, this product and this summation can be interchanged using this formula. I have a video for this in this channel that proves this equality. This equals this. Here the sigma is after the product, but now sigma is before the product. I in the products here and here are from 1 to n. Nothing changes about I. But k, which is the index of the summation, changes to a function f from nn to nr. And all k's that appear in these summands will be replaced by f of I. I is the index of the product. Tk, tf of I, tf of I. And there's not any other k, so this is converted to this. Now we move this into the summation. Nothing changes. And then we interchange these two summations. Nothing else changes. And now we factor this out of this summation, and this is obtained. In fact, we add a parenthesis here, and we get this. All these calculations, in fact, are not needed if we know that f is a polynomial of degree at most n. This, in fact, confirms that f is a polynomial of degree at most n of r variables, a polynomial of r variables of degree at most n. Therefore, if it is 0 at n plus 1 to the r different points in a to the r, it is identically 0. If f of x is a polynomial, like ax2 plus bx plus c, and this polynomial is 0 at 3 different points, x1 equals 0, fx2 equals 0, and fx3 equals 0, and these numbers are different, then we can deduce that f equals 0 identically. Because if f is not identically 0, f can have at most 2 zeros, but when it has 3 zeros, we deduce that f is identically 0. Here, f is a polynomial of one variable, r is 1, of degree 2, n equals 2. The same is true for the polynomial f of r variables of degree n. If f is 0 at n plus 1 to the power of distinct points, then f is identically 0. This is a well-known theorem about polynomials with r variables of degree n. We use that theorem here. Thus, f is a polynomial of degree at most n. Therefore, if it is 0 at n plus 1 to the r different points, I can say distinct points in this set, it is identically 0. If f is identically 0, ax equals bx, this equation, has no invertible solutions, and so a and b are not similar. So all we have to check is that if the function f is 0 at n plus 1 to the r distinct points in R to the R, in R. Otherwise, they are similar. If f is not identically 0, then a and b are similar. Thus, we need to check whether f is not 0 at all points in this set. How is this defined? Just like R to the R. In fact, this is a subset of this. It has n plus 1 to the r distinct points, so we need to check whether f is not 0 at these points. Of course, we know that f of 0, 0, 0 equals 0. In fact, we don't need to check this point in this set because we know that f of this point is 0 by this equation. If all tk here are 0, then f of t1 to tr is 0 because this product is 0. So in our algorithm, we don't need to check this one. We just check other points in this set. It becomes n plus 1 to the r minus 1 points. We have to check the value of f in these points. The following C# function checks if the matrices A and B are similar. Let's see this function in Visual Studio. The function is named R similar. This means if the matrix A and the matrix B are similar. Now let's read the algorithm. First, we get a basis for the space of solutions of the equation ax equals xb. Here we get a basis for the space of solutions of this equation. We get a basis for the space of solutions of this equation. This basis is stored in this list. Let n be the number of rows of A, which is equal to the number of columns of A. Let R be the number of members of this list, the rank of the basis, the number of basis members. So R is the number of basis members. In fact, we have this set, and R is the number of members of this set. If R equals 0, if this set is empty, it means that the basis is empty. So this equation has only one solution. This solution is in fact x equal to 0, and x equal to 0 is not invertible. So A and B are not similar. So if R equals 0, if the basis set is empty, return null. Null means that A and B are not similar. So in this case, null is returned. Otherwise, there will be at least one member in this list. There will be at least one member in the basis. We need to find this sum first. We define a matrix called sum. Sum, in fact, is this matrix, provided that it is invertible. If it is invertible, sum will be returned. So we will find an invertible x here, and x will be returned, and A will be x, B, x inverse. So if A and B are similar, this function will return x. Otherwise, it will return null if it doesn't find an x. Then we define the function f. We define sum to be a matrix, an n by n matrix, because this is an n by n matrix. Then we form this sum here with this loop. I add these summands here, tk times tk, tuple tk times list tk. Tuple tk here represents tk, which is given to this function as a parameter. Tuple tk times list tk, we know that this list represents this set. So list k is in fact tk. Tuple k is in fact this lowercase tk. Tuple k is lowercase tk, and list k is this uppercase tk. This summation is formed, and what is returned is the determinant of this matrix. All this is a matrix. F is the determinant of this matrix. So f of these tk's is the determinant of this matrix. So F is defined to be the determinant of this matrix. Now we must check that F is 0 at all points of this set. So we need R iterated fors, but R is a variable. And we cannot write a variable number of iterated fors in C#. So we need to somehow simulate these iterated fors, for example, using a recursive function. I use the recursive function check to simulate R iterated fors. We define the tuple be an array of R numbers. These numbers are to be from 1 to n. Tuple depth equals I, because our tuples are members of this set. In fact, by a tuple I mean this. T1 to Tr is a tuple. Our tuples are going to be all members of the set. We need to iterate over all of these members. To this end, we use R iterated fors made by this recursive function check. This tuple will represent a member of this, and for any member of this here, we check. If it is the first tuple, which is this 0 tuple, we do nothing because we know that F is 0 at this point. For the next tuple in this set, we check that if F of that tuple is not 0. If it is not 0, we return true. When this F is called, this sum defined here gets a value, and its determinant is calculated, and we find that this determinant is non-zero. So true is returned, and now we have the summation, which is invertible because its determinant is non-zero. So if check returns true, it means that we have found an invertible summation like this, which is a solution of this equation. So if true is returned, we have found what we were going to find: a tuple at which F is non-zero. If F of tuple is non-zero, return true, and now we have the tuple. And when check returns true, we return the sum, which is the invertible matrix that is a solution for this equation. Sum is returned. But if F is 0 at all these tuples, which are a member of this set, then we find out that F is identically 0, and this means that A and B are not similar. In this case, null is returned. You know that when this function returns null, it means that A and B are not similar. Here, the algorithm is complete. We found an algorithm that checks if the matrices A and B are similar. And if they are similar, we have an X that satisfies this. Let's check this algorithm. I defined n to be 4. The matrices will be 4 by 4. I define a random x1. x1 is an n by n matrix. N by n. X is randomized. It means that all of its entries will have a random number, and then it is printed. X is printed. Then we define a matrix B. B is randomized, and A is intentionally defined to be similar to B. So we defined a matrix X1 randomly, a matrix B randomly, and a matrix A which is equal to x1, b, x1 inverse. So A and B are chosen to be similar. x1 is random, b is random, but A is defined such that x1 is a solution of the equation A equals xbx inverse. x1 is a solution to this. A and B are similar, and so A and B are defined to be similar matrices, so we can check our function. We define A to be x times B times x inverse. We print A, we print B, so we know what are these matrices. Now we know that A and B are similar. Now we can check our function called R similar. You know that this function returns null if they are not similar, and returns this sum, in fact this x, if they are similar. We name what is returned x2. x2 is what is returned by this function. If x2 is null, then the matrices are not similar. Print matrices are not similar. But if it is not null, then it is a solution of this equation. We print x2 that is a solution of this equation, and we print this. We print x b x inverse, x2 b x2 inverse. We print it. It must be equal to a. So what is printed here must be the same as what is printed here. This must be equal to a. Let's run the program to see the results. You see a random matrix x1, 4 by 4. A is defined to be similar to b. A and b are defined in such a way that they are similar. Now, x2 is what is returned by this function. You see x2 here. And x2b, x2 inverse is printed here. We see that this equals a. So x2a, x2 inverse equals a. They are the same matrices. So x2 is a solution of this equation, just like x1. x1 and x2 are solutions of this equation. But you see that x1 is different from x2. So this equation can have more than one solution. In fact, it can have infinitely many solutions. x1 and x2 are two examples. You see that x2b x2 inverse equals a. This is a. You see, the same as a. So these matrices are similar. This means that this algorithm works. Let's change one of the entries of A, for example. A2, 3, the entry on row 2 on column 3. Let it be 8. I think now they cannot be similar anymore. We defined A to be x, b, x inverse, but then we changed A, so it's maybe no longer similar to b. Now we check what is returned by this function. I run the program. Matrices are not similar. I move this command here. So A and B are printed after this change. Then I run the program. You see, A has a changed entry, and the result is that the matrices are not similar. So A and B are no longer similar after this change. So it seems this algorithm is correct, but is it the best algorithm? I don't think. There may be faster algorithms. I just improvised that algorithm and it works, and I have not found any other algorithm on the internet, and also ChatGPT could not find a deterministic algorithm to check if two matrices are similar, so I tried to do that. I hope my work is useful for you. Thank you for watching this video. Like, subscribe to the channel. Thank you.